Thanks a lot. So first of all, thanks a lot for your invitation. Thanks for having me here today. And my name is Denis Korzhenkov, as Olga had already said, and I'm one of the authors of Mobile Video Diffusion paper. And today we are going to discuss this work of our team at Qualcomm. So probably most of you, if not all of you, are fascinated with the recent progress of video generation models, but there is one little issue. Most of these models are too large to deploy them on your local device. At least you need a pretty good consumer-grade GPU at your working machine to run such models locally. And if it comes to deploying to mobile devices, to low-edge devices, then things are even worse. It is pretty difficult to find an open source or even closed source model that is able to run locally on device. And since the release of Sora model more than a year ago, the video generation field pivoted to the usage of diffusion transformers models. But if you look closely at papers which describe different approaches to deploying generative models on device, not even for video, but even for image generation, then you will see that most of these works still continue using UNet type architectures. So the answer is pretty simple. Transformers require quadratic usage of memory unless you apply a set of tricky optimizations. But on device, these optimizations are somewhat harder. So still, most on device people prefer to use UNet type architectures. And we followed the same path. And we have chosen the Stable Video Diffusion model, which was open sourced, as a stem for our deployment to the device. In this slide, you can see the table from the very nice SFV paper by Snap, which explore different approaches to the step distillation of the original Stable Video Diffusion model. So SVD is an image-to-video model. Unfortunately, only image-to-video checkpoint was released, and we don't have any public access to the text-to-video model. So it is a diffusion model. And by default, it requires 50 denoising steps at inference time to produce a video. And the first step to deployment is usually the reduction of the number of steps, because no one wants to wait that much to generate a video usually. So in this SFV paper, the authors proposed a pipeline for step distillation. So they distilled an SVD model to a single step. So you can see in the bottom line that actually their quality of generation as measured by FVD metric is not significantly worse than the original model. So, but unfortunately, this architecture is still too large to run it on a mobile device. So as you can see, when we tried to port it on a mobile phone, we faced the out of memory error. And yeah, that's it. So it turns out that it is not enough to decrease the number of steps. You also need to do something with the architecture if you want to produce a video on device. And in our work, we explored a set of optimizations which finally allowed us to run the slightly changed version of this model on an Android mobile phone. And so as I have said, one of the first steps is to apply this adversarial single-step distillation, which is number 4 in this slide. But during this presentation, we will discuss other approaches that allowed us to reach our goal. So first of all, the Android NPU has a very low amount of available memory, only 8 megabytes, if my memory serves me right. So unfortunately, we found that it is necessary to decrease the resolution of the output video to feed these memory constraints. So our first step was to decrease the resolution from 1024 pixels to 512. It turned out that although originally SVD used to be a low resolution model that was fine-tuned for high resolution afterwards, as the authors had described in their paper, after we tried to generate low resolution videos, we realized that actually the model had forgotten everything about the low resolution generation. And we were to fine-tune the model to restore its capability to produce low resolution videos at resolution of 512 by 256. But with the help of this low resolution fine tuning, we were able to decrease the amount of flops from 45 to roughly 9. After that, to further decrease the computational requirements, we decided to explore additional downsampling layers in the UNet architecture. So first of all, I need to say that the SVD architecture doesn't apply any downscaling along the temporal axis. So in the UNet architecture, they downsample and afterward upsample only spatially. And the number of latent frames is always equal to 14. So we explored if we could downsample temporally also, and we found it possible with the neglectable loss of quality. So as if you see on the right, if we apply this downsampling operation, the quality degrades from 133 to 138 as measured by FVD. We also explored if it is possible to downsample spatially to apply an additional downsampling layer in addition to all the layers which already exist in the UNet. But we found that in this case, the gain in latency is contradictory to the loss of quality. So we decided to stick with the temporal downsampling and upsampling only in the revised architecture. The next point is probably not that significant for people who usually work with GPU, but perhaps surprisingly, it turned out very actually crucial for the mobile deployment. So as I have already said, the open sourced SVD checkpoint is an image to video model. And the conditioning on a first frame is conducted in 2 ways. First, now, the latent first frame is concatenated channel-wise to the noisy tensor, which is denoised using the UNet. But also there is a clip embedding of this conditioning frame, which is used in the cross-attention operation. Originally, as I've also have already said, SVD used to be a text-to-video model. And this cross-attention operation had a lot of sense because this was the way to extract information from the textual description to the image tokens. However, since now it is an image-to-video model, we only have a single token, a clip embedding of the conditioning image. And it turns out that the cross-attention operation is actually redundant now because you have the queries, and these queries are image tokens in the UNet, but the keys and values consist of a single token of this clip image embedding. And this makes the whole attention operation redundant. So it is basically a no-op. You can just compute the value part of the attention operation, and here you are. It is just enough to replace all this operation. However, when we tried to deploy our model on device without removing this redundant cross-attention operation, we faced that such a corner case for softmax operation in the compiler required a lot of memory for some reason. To be honest, we don't really understand the reason for such behavior, but our model still produced the out-of-memory error when we tried to deploy it without this modification. And for smaller resolution, you can see on the right that the model without this optimized cross-attention requires so many softmax NPU cycles that but they are basically unnecessary. You can avoid them without any loss in quality and precision. Just you can remove it. So after we realized that this can be done, and after we applied this optimization, we really finally unlocked the on-device deployment of the device. And all the further optimizations only targeted the decrease of mobile latency to produce the video. And our first, maybe non-trivial, I can say, optimization was the so-called channel funnels. Basically, channel funnels are learnable adapters which allow you to decrease the number of channels in your network. So to decrease the width, as some people say. So on the right, you can see the scheme of these channel funnels. Basically, if you have 2 sequential linear layers, let's start with linear layers for simplicity, we can train these adapter matrices F1 and F2, which project the activations to the space with smaller number of channels. And you can train them either alongside with weight matrices at training time, or you can freeze the weight matrices and train only the final matrices. And at inference time, you can pre-multiply these weight matrices with the learned final matrices. And after that, you just have a latent space, an activation space with fewer channels, and your computation is now much faster. Of course, it depends on the factor of channel reduction. But after we introduce this scheme, we need to recap that basically we are working with a pre-trained model. And so if we want to somehow fine-tune this model, we need a good initialization for these final matrices. And we propose a so-called coupled singular initialization scheme, which relies on a truncated singular value decomposition. Basically, again, let's consider two consequent linear layers. So we take the weight matrices of these two linear layers and ignore the nonlinear function in between. So we know that different simplification assumptions, simplified assumptions are actually widespread for the purpose of initialization in deep learning. So we also follow the same path. After that, we apply the truncated SVD to this product of two weight matrices, and we initialize funnels in such a way that the resulting product with ignored nonlinear function, with ignored activation function, will coincide with this truncated SVD output. On the left, you can see the comparison of our proposed CSI coupled singular initialization scheme with the random initialization of funnel matrices. So as you can see, the random initialization with the came in here initialization scheme produces actually awful results in our experiments. Of course, I don't know, maybe if you change the training recipe or if you train for a significant amount of time, maybe this can be improved. But in our experiments, the result of random initialization was really awful. And in contrast, our proposed coupled singular initialization provides a really good quality, even if you reduce the number of channels up to the 3/4. So the fun factor of 0.25 corresponds to the 3/4 of the channel in between removed. Also, I forgot to say that we apply this channel funnel scheme to the attention operation, so to the query and key matrices inside the attention. So in this case, you don't even need to worry about the activation function in between, because this is just inner product of two matrices. But we also tried the same scheme for convolutions and for residual blocks. And as you can see on the right, basically it also works, but the gain in latency was not that good. So we decided to stick only with funnels applied to the attention operation. Also, as an alternative to our proposed funnels, you can think about the truncated singular decomposition of individual layers. So basically, you have a single linear layer, and you decompose it into a low-rank product of two smaller linear layers. But as you can see, if you have the equal number of flops, so for 8 flops, our funnels method has lower latency, and so it seems that it is preferable for on-device deployment than the regular truncated SVD. And as the last optimization, let's look at the temporal block inside the UNet architecture of Stable Video Diffusion. So it has a pretty complicated architecture, these temporal blocks, which is illustrated in this diagram. So you have the output of your spatial layer named XS, and this tensor XS goes to the temporal layers inside a temporal block, and then it is summed up with XS, and then there is also a learnable scalar alpha, and you have one more mixing operation with the help of this learnable scalar. But as I have put it in the bottom of this slide, you can simplify this operation. And it turns out that actually this XS output of spatial layers can be thought of as an untouched tensor. And you have this residual connection with learnable 1 minus alpha multiplier, which is applied to the output of temporal blocks inside the single block of this UNet. So, and you can think like, okay, this means that if 1 minus alpha multiplier is low, if it is close to 0, then basically we can prune the temporal block and retain only the spatial block. But in addition, we can not just prune the temporal blocks with the lowest value of 1 minus alpha, but instead we can fine-tune the whole network by using the binary gates Z, so which are illustrated with this green slider in the, on the right. And we apply this binary gates 0 hat, which are equal to 0 or to 1. So these are discrete gates. And we fine-tune our network with the help of these learnable discrete gates. The whole idea is to retain the given number of temporal blocks. So we have this budget of n temporal blocks, which we want to remain in the network, and we want to prune all the blocks other than these n blocks. So if you think about this from the perspective of sampling without replacement, if you learn a probability pi for each temporal block, then in case of sampling without replacement, the sum of these pi values should also be equal to n, because for each sample, the sum of indicator values z1 plus zn is equal to n, then the expectation should also be equal to n, then the sum of probabilities should also be equal to n. So to find such inclusion probabilities pi which have this property, we apply the differentiable constraint optimization. So this is a problem which can be solved in a closed form, fortunately. So for each temporal block, we learn some scalar importance value q, and each training iteration, we transform this set of q values into the set of proper inclusion probabilities pi. And by proper, I mean that the sum of all these inclusion probabilities is equal to n. After we have obtained the set of these proper inclusion probabilities, we sample without replacement these binary gates for each temporal block, and exactly n binary gates are equal to 1, and all the rest of these gates are equal to 0. And after that, we apply this binary gate, these discrete gates, as an additional multiplier in this residual branch of the temporal block. And by using this technique, we are able to learn the n blocks which should remain in the network. And we learn this in an end-to-end fashion. As an alternative, as a baseline, you can think about just imposing L1 penalty on these 1 minus alpha values for each temporal block. But as we show in this table, it turns out that if you want to prune the same amount of layers, so basically if you want to prune 30% of temporal blocks, it turns out that our method with learned binary gates is much more effective. Okay, so let's go to the final results. So in the bottom of the table, you can see the results of our optimization for the lower resolution. So as I have said in the beginning, if we use the original SVD model in lower resolution without any fine-tuning, it has the quite bad FVD of 366, but after some fine-tuning, this number is improved up to approximately 200. Also, as I have said, the optimized cross attention has little to no effect for the GPU latency, and the GPU latency decreases only from 82 to 76 milliseconds. However, for the on-device deployment, this is crucial. Finally, we are able to run the model on device and do not get this out-of-memory error during the compilation. Then it turns out that our non-trivial methods like channel funnels and learnable block pruning help us to further reduce the mobile latency by 31% after the temporal multiscaling was applied. Also, as a proof of concept, we applied the same set of optimizations to the original SVD model to check if they have any sense in case of high resolution generation. And in the top of this table, you can see the results of our MobileVD HD model, which produces the videos in the high resolution of 1024 pixels. And as you can see, of course, the quality is slightly worse in terms of FVD than of the original SVD model, but it is still quite competitive. In this table, you can see the results of vBench evaluation with the more recent toolkit of metrics for video generation. And if you look if you pay some attention to this table, you can think about this influence of this motion bucket hyperparameter. So the Stable Video Diffusion model cannot be controlled with the textual prompt. But for controlling the speed of motion in the generated videos, it has a hyperparameter called motion bucket. Unfortunately, the authors of Stable Video Diffusion paper haven't released the speed estimation model, which they had used to estimate this motion bucket in the train videos. And we were to develop our own method for measuring this motion bucket, for estimating the speed of motion in the videos. And for that reason, after fine-tuning, we could not use this default motion bucket value for generating videos anymore, because the default value of the open source model of 127 just had no sense with our new definition of motion bucket. So for the purpose of FVD evaluation, as I have shown in the previous slide, we just computed the median value of this motion bucket on the UCF dataset, which was used to measure FVD. But for vBench evaluation, since it also tries to evaluate the dynamic degree of the generated videos, we simply played with different values of this motion bucket hyperparameter. And as you can see, if you use the motion bucket of 40 for our MobileVD model, then you can achieve the dynamic degree of 95.77, while the original SVD model with the default motion bucket of 127 had a dynamic degree of 95.69. Also, you can see from this table that if we produce videos with more vivid motion, so with motion bucket of 40 in comparison with 20, then the quality of the frames slightly deteriorates. For example, you can see the drop in aesthetic quality or imaging quality metrics of vBench toolkit. So now let's have a look on some results of our model. So in this video, we compare our model with the released videos. These videos had been released by the authors of SFV paper. So you can see that our MobileVD model produces videos which are quite competitive to the videos produced by other methods. So this is the comparison with the original SVD model. Unfortunately, I can admit that our method produces slightly worse quality on human faces. Probably this is due to the issues with our training dataset, but with other objects and textures, it is usually more or less fine. In addition to the SVD and SFV methods, which I had discussed earlier, we compared our method with a more recent SnapGenV model. SnapGenV is a very recent architecture and method from Snapchat, from Snap. It is a specially tailored architecture for on-device text-to-video generation. In contrast to our work, SnapGenV is a model which, with an architecture which had been chosen using neural architecture search, and it was trained from scratch to be deployable on a mobile device. So, as opposed, we use the open source checkpoint to train our model, basically to fine-tune it from the release checkpoint. And it seems from the technical report of SnapGenV that in the end, we require significantly fewer computational time and fewer GPU time to get our model in contrast to SnapGenV. So for the practitioners with lower computational resources, our approach seems more suitable, maybe. So one more slide with the comparison with SnapGenV. And basically, this was the last slide. Thanks a lot for your attention, and I'm glad to answer the questions.